Welcome back. Um, we'll be talking about steel structures. Um, this is my first session on steel structures. I'll be using the 15th edition of SCM, or the Steel Construction Manual. I'm using this version because this is what is being used in the PE and SC exams currently. We'll be talking about chapter D, which is in the specification, which is about tension members. And we'll also be talking about part 5, which is again design of tension members, right? Again, the intent of these videos is the following: all the structural codes like ACI, AISC, they are very heavy on text but light on visuals. My goal is to take these dense, complex clauses and bridge the gap with simple hand-drawn sketches. We'll not be doing a formal presentation, a nice PPT, like an office level presentation, but I'll be layering these chicken scratches on the code canvas. I'll be drawing things on the code canvas because that is what you get to see in the exam. You will not have PPT, or this is not an open book exam wherein you can um, get your books and all that, right? So I'll be layering these chicken scratches on the code canvas, and I'm trying to transform all these abstract rules into clear mental images. This visual association will make it much easier for you to recall any specific requirements when you're under pressure in an exam setting. For example, if you have to visualize the gross area versus net area of a tension member, then hopefully these sketches that I'm going to draw today are going to help you do that. Okay. So there's a lot to cover. The idea is also to do some problems, worked out examples on this. So let's get started. So here is the steel construction manual. If you look at the bookmark side, you will have a bunch of parts. I think there are 17 parts. Um, each part is dedicated to a certain topic. For example, part 5 is what we'll be looking at today. And this is about the design of tension members. Um, but this part will only have minimal information about some definitions, and then the most important thing in these parts is the design table and um, the omega factors and phi factors and all that, right? But the actual stuff is being discussed. If you have to get in depth, then you'll have to go to the specifications, which is part 16. So under part 16, if you go to chapter D, that is where all the uh, nice information is provided, right? And there's also a little bit of information in the commentary section of the code. Um, but we will be focusing on part 5, design of tension members, and we'll also go to uh, design of tension members, chapter D. All right. So not too much information is in part 5. Let's start here. So this is part 5, and you see design of tension members. They're talking about gross area and net area. No formulas are provided. These are just definitions, right? And they're talking about two primary limit states, which is yielding limit state and rupture limit state. When it comes to tension members, these are pretty straightforward problems, unlike compression members, which get subjected to local buckling or global buckling, or sometimes torsional buckling or flexural torsional buckling and all that. Tension members have two main limit states. We'll talk about that in detail. So that is what is being discussed here. There is a yielding limit state and there is a rupture limit state, and these two limit states happen on different areas, and that's why there is a definition for gross area and net area here. Okay, and then we get to um, we'll not talk about this again in these sessions. We'll not talk about every little detail in the code. That will make the sessions pretty long and then exhaustive, and they're not even needed for exam. I mean, I'm keeping the breadth level exam in mind, breadth level PE, breadth level SC, and regular day-to-day office job kind of scenarios in mind. Okay, so we'll not talk about this special requirements of heavy shapes. but then we'll briefly look into these tables. These are not very useful for an exam. These are useful in an office setting, because there is an underlying assumption in these tables which may not be the case for a problem in an exam. Okay, so that's about the introduction. Um, for now, just understand that there are two areas that we need to calculate. There is something called gross area denoted by AG, and there is another area called net area, which is effective net area, not just net area. Effective net area, which is AE. Okay, and to calculate this AE, you will have to understand what is U, and you will have to understand what is A net. Okay, so we'll talk about those things, but then all that this section tells you is the gross area AG is available here, which is chapter B, and the net area AN is available at a bunch of locations. So it is not giving you any useful information about how to calculate those areas, but then it is giving you references as to where you can excuse me, where you can find all this. Okay, so again, so let's talk about what um, you need to really understand what. Uh, okay, so what this is saying here is, for now, imagine that this is how you calculate your strength in yielding. Okay, so this is how you calculate your. Remember, we talked about limit states. There is a yielding and there is a rupture. This is how you calculate your yielding strength, and this is the formula that you use to calculate your rupture strength. Um, so this section is just saying that for that to happen, then you need to satisfy this criteria. If you satisfy this criteria, this is just a function of your AE, AG, FY, and FU. Then this is applicable. Okay, but then again, this is not useful in an exam setting. In an exam setting, we will have to calculate the yielding strength separately, the rupture strength separately, and then compare those two and pick the value whichever gives us a lower number, right? So again, this part, like I said, part two, this is not useful. There are design tables, for example 6.2, and then there are a bunch of other design tables, but they come with an assumption, very important assumption, that this is the effective net area is assumed to be 0.75 times of A gross. Again, this assumption is good in a practical, in an office setting. If you're a employee working on steel structures, then this is a good guideline or starting point. um, but it is not useful in an exam setting. In an exam setting, rarely your AE will be 0.75 times of AG. So all these tables here are pretty much useless in an exam setting. Okay, we'll just hold your horses. We'll talk about AE, we'll talk about AG, we'll talk about A net, we'll talk about U, we'll talk about X bar, we'll talk about L, and all these things. um, um, but that discussion is in chapter will be made clear in chapter D. But now currently we are just going through the part 5. Okay, then there are again a bunch of tables available, but for different shapes. For example, W shape, and if you satisfy that criteria there, right? The relationship between AE and AG, then these tables are useful. But and for this one here is for angles. If your tension member is an angle, if your tension member is a T shape, if your tension member is HSS, round or square or pipe. But for exam, all these are literally useless because they all have an underlying assumption, and um, which is most of the times which is not the case, right? So we will learn to do the long form, two simple formulas. That's about tension members. We will learn to do all that and then come back to these tables if needed. Okay, so let's talk about the theory of tension members real quick. Again, this is not a university level class or something. All that we are trying to do is to quickly cover all these terms. Okay, so if you have a tension member, what that means is you have a let's say you have an angle like that, and then and that angle is being subjected to tension. Correct. So that's what a tension member is. When that happens, this angle might have a couple of bolts like that, right? Might have some, might be getting bolted to a gusset plate here, might be getting bolted to something else which is here. So that bolt is traveling through one leg, and this bolt is traveling to the other leg, right? So there is a there are two primary uh, failures that can happen. One is the yielding failure, yielding, and then is a rupture. The second one is rupture, right? So you have to remember that yielding happens uh, on the gross area. For example, let's take a simple plate. Let us say here is a gusset plate, and to this gusset plate we are adding another plate, right? Instead of welding the plate, we decide to put a bolt like that, right? Um, so the yielding failure is something that happens. Now we are talking about the tension member itself. This is the member that is subjected to force. That is the tension member that is on focus. We are not talking about the gusset plate here, right? So when you apply a force like that, then the material itself can yield. For example, let's say this is cross section 1 1, which has all the uh, there is a gross section. There's no reduction in area because there is no bolt hole cutting this particular section there. So if you take the section of if you look at it from this particular view, then it is a simple plate like that, right? And this area is nothing but the width of the plate. Let us say width of the plate is that, and then this is your thickness of the plate, correct? So width time thickness is your so a gross is nothing but your width times the thickness of the plate. So that is your A gross. So yielding has to do, so E is a function of yielding strength is a function of your A gross. Okay, and yielding strength is also function of your yield strength Fy, not the ultimate strength. Correct. So in other words, and yielding strength is also a function of your I mean if you are calculating the design strength, then your yielding strength, you'll also have to account for the strength reduction factor, like how we did in concrete, right? Let's call it Phi t. So in other words, yielding strength is a function of all these things. Ag, it is a function of your Fy, and it is a function of Phi t. Okay, and I mean we're talking about LRFD here, so we're talking about Phi t. So it is, if when you look at the finer formula, your ultimate load, let us say the ultimate tensile load, should be less than phi times of your um, load in I mean nominal load in tension, correct? Or nominal strength in tension. Okay, and that nominal strength is nothing but your phi t times your Fy times your Ag. Okay, so that is your strength from yielding point of view. Okay, so like I said, it is a function of Fy, it is a function of Ag, and it is a function of your phi t. Phi t for yielding, because it's not I mean it is a limit state which gives you sufficient warning, it is around 0.9. So 0.9 Fy times Ag is your design strength, not the nominal. If you scratch this off, then that is the nominal strength, right? But then we reduce it with a factor, and you call it your design strength. So 0.9 Fy times of Ag is your um, yielding strength, right? And the next limit state is called rupture limit state, and the rupture limit state happens on a net section, right? So for you take the same, that means it'll happen at this section here, right? So if you take a cross section there and then look at from this view here, so you have your plate which is that thick, but then there is a bolt hole um, uh, which has been cut from the plate, right? So this particular area there, we'll see how it can be calculated. But if this is the width of the plate, so from the width of the plate you need to subtract the size of the hole. Okay, and we'll talk about how the hole size can be calculated. It's not just the diameter of the bolt. it is the nominal diameter of the bolt plus a certain number. Okay, we'll plus a 16th of an inch, but then we'll talk about that in detail how to calculate that. But for now, assume that you know the width and you know the diameter of the hole. W minus diameter of the hole times this is the thickness of the, let us say this is the thickness of the plate. So times TP will give you your A net. Okay. So rupture is a function, the rupture strength is a function, this particular rupture is a function of something called AE, and it is a function of U, sorry, it's a function of AE has U inherently, so let's do that. So your rupture is a function of your net area, and it is also a function of something called a shear lag factor, and it is also a function of your FU, which is the ultimate strength of steel. So in short, yielding and rupture, right? So yielding is a function of, I mean, yielding is you take your phi value, you multiply that with your Fy, and you multiply it with your gross area. Whereas this one, you take your phi value, which is a different phi value, you multiply it with your Fu, and you multiply with something called Ae. Okay, and that is what is being discussed here. So if I go to chapter D, tension members, so this is what is happening here. So this is tension yielding Fy times of Ag, and here is your phi t, right? So in other words, this is phi t times Fy times Ag, and if you are doing ASD, then you just you calculate your nominal strength and divide that by omega to calculate your design strength, and that omega is 1.67. Okay. Tensile rupture is happening on the net section, and that is AE. Okay. So remember again, AE has to do with uh, so that hatched portion there. Okay. Whereas AG has to do with the full section without the deductions. Okay. So this is we'll see how AE can be calculated. AE is not just net area. You will have to there's I mean, if we scroll down further, you will see all those definitions. Okay. So that is what is happening here in this section. Now we scroll down, we find out that AE has to be calculated as AN times U. AN is the net area, and U is something called a shear lag factor. Okay. So to calculate net area, you'll have to understand two things. Let's say you have a let's say you have this is the plate, and let us say this is the tension member under consideration. Here is the P, and there are two bolt holes. Okay, and we are interested in calculating the net area of this section, right? That means if you take a section there, section 1 and 1, you will see something like this. You will see the plate. Let us say this is W. The width of the plate is W, but then there are two bolt holes that are cut in that particular plate, and we are interested in calculating the net area of this particular plate. Okay, we know the thickness of the plate, and we also know the bolt diameter, d bolt. Okay, so if the bolt diameter, if this d bolt is less than 1 inch, right, then the whole diameter, which is what we need, the whole diameter is nothing but the nominal diameter of the bolt, which is dB. If dB is the diameter of bolt, plus 1 by 16 is the nominal diameter whenever your diameter of the bolt is less than 1 inch. So plus another 16th of an inch. Okay, but if your d bolt is greater than 1 inch, then the definition of nominal diameter of the bolt is itself is different. So d hole is nothing but your nominal diameter plus 1 by 16. So this 1 by 16 remains the same. Okay, but your definition of whenever your bolt diameter is greater than 1 inch, the nominal bolt diameter is the bolt diameter plus 1 by 8th of an inch. So this is nothing but dB plus 3/16 of an inch. So D hole is not depends upon, so D hole depends upon, is a function of your diameter of the bolt. Okay, one more time, if D bolt, if the diameter bolt, let us say you are using 0.75 inch diameter bolt, if your D bolt is that much, okay, then your, in this case, your nominal bolt diameter is that much. So 0.75 plus 16th of an inch. But then you have to add another 16th of an inch to calculate your D hole. Okay, but if your DB, the D bolt that you're talking about is if your DB is, let us say, 1.25 inch, okay, which is greater than 1 inch. If your DB is greater than 1 inch, then your nominal bolt diameter, which is this term here, itself is inch and a quarter plus eighth of an inch. To that, you will have to add another 16th of an inch to calculate your D hole diameter. Okay, so that is an important thing to remember, because if you're wrong here, then you're wrong in terms of your in calculating the net area. If you are calculating your net area wrong, then you're calculating the rupture strength wrongly, and then you compare that with something else, and you get into a wrong conclusion. Okay, so that is what is happening with this one. So in this case, if I have to calculate the net area, we're not talking about effective net, just net area. Then I take W minus, I subtract the number of holes. In this case, multiply that with the thickness. So W minus dh is from, depends upon if my diameter is less than 1 inch or if my diameter is greater than, diameter of the bolt is greater than 1 inch. So there are two DHs in this case, right? And then I multiply that with T, okay, to calculate something called A net. Okay, so A net is only a portion of the story. Once I calculate my A net, I have to multiply it with the factor called shear lag factor. Again, this is not a steel theory, so we will not get into what shear lag is and all that. But just assume, for example, if you have a plate like that and you have a plate like that, and they are connected like this, and this is a tension member, meaning there's a tension here. A portion of when this plate is trying to be pulled in to the right, a portion of this plate is not participating in taking the tension at all, right? um, so you need to reduce the net area of your member. You calculate net area, but then you reduce it by a factor called U, and then calculate your AE. And this AE is what is used in your rupture calculations. Remember, rupture happens on the net section, and the rupture strength is nothing but the strength reduction factor in rupture, Fu times of your AE. This is not a net, this is a effective net area, and AE is nothing but a net times of U. So a net is your, if you have a plate like that and a bunch of holes like that, this hatched portion is your a net. So you calculate a net, which is a function of your D hole and the width of the plate and the thickness of the plate and all that. But then you multiply that a net with with a factor called U to calculate your AU value. Okay. Now, how do you get the U value? The U value depends upon what is your shape and how it is connected, to how the shape is connected to the adjacent gusset plate or something like that. So the U value primarily is in this particular table here. We'll take a look at the table D31 and talk about those things in detail. And this is a very important table for the exam. There will be definitely questions, definitely instances wherein you have to come back and use this table here. Okay. So firstly, if you zoom out a little bit, there are how many cases? From here to here, there are 8 different cases. So the problem that you have in the exam is going to fall in those cases. Okay. And out of those cases, the first case is almost useless for us, right? So this one here is saying when you have a tension member that is connected to that has all its elements, connected, then the U value is 1.0. So the exact verbiage is all tension members where the tension load is transmitted directly to each of the cross-sectional elements by fasteners or welds, U equal to 1.0. What that means is, um, if we go here, let us say you have a plate like that, gusset plate, right? And then you have your uh, member like that. You are subjected to tension. This particular thing plate is welded here, and is welded here, right? So this thing only has one element because it doesn't have a web and a flange and all that. This only one single plate, and the load is being applied, and that single all the elements in this particular component are connected to the gusset plate. So when you encounter a scenario like this, you don't have to do any reduction. That means your U value is equal to 1. Okay. Now you might have a I section. Let's say you take an I section like that, and you connect the flange with to another plate. You connect this flange to another plate. You connect the web to another element, right? So these are all connected. This is connected. This is connected like that, right? So when that happens, I section has a flange, a web, and another flange, and all these members are connected to an adjacent member. So when that happens, again, your U is 1.0. Okay. So if you in a T scenario, take a T like that, correct? U equal to 1.0. Let's say you have this thing connected, you have the web connected to something else, right? And then the tension forces are being applied normal to the screen. In this case, your U equal to 1.0. Okay, so that is what case 1 is about. It is talking about shapes wherein all the elements are connected, all the elements of that shape are connected to um, so this is the first element, this is the second element, this is the third element. All these elements are connected to something else through welds or fasteners. Maybe you're welding it here, or you're just fastening it here. Then U equal to 1.0. Okay. Um, so like I said, case 1, the easiest case. If you have that, you must be happy in your exam, right? Again, where tension load is being transmitted directly to each of the cross-sectional element component by either a fastener or a weld. Case 2 here is the most common case, and you will definitely have problems case like this, wherein if you see this picture here, they have provided nice pictures there. You have an I section. This is the I section. It has a flange. It has a flange at the bottom, and it has a web. But only the flanges are connected through plates. The plates, that means you are applying the load like that, but it is connected only to only at the top flange and the bottom flange. The web element is not connected, right? So when you have a scenario like this, when all the elements of the tension member are not connected to transmit the load, then your U value becomes a function of something called X bar and L. Okay, and X bar is nothing but, if I blow this image a little bit, uh, you see that here is your this is the uh, so this particular point here is the centroid of that particular T shape, right? So from the centroid to the um, shear plane, uh, where is the load being transmitted? Load is being transmitted there. So that distance is your X bar. Okay. Now, if you have an I section like this here, again, X bar, this is an important thing, I section. So you're talking about the centroid of this particular C shape here, right? Only one half of the I. You're talking about the centroid of that C, that might be somewhere here, correct? From the centroid to the axis of the symmetry, that is your X bar, right? From the centroid of the shape to the axis of symmetry, that is your X bar. If you have an L shape like that, L is connected here, so that is the location to which the shear is being transmitted, correct? So you're applying, in other words, this one, if you see it from this view, looks like this is an angle. It's an angle like that, and it is connected to maybe it is connected to a plate like this, correct? And it is just connected only one element of this angle is connected, and the angle is subjected to axial load like that, right? In that case, you need to find out what your x bar is, because not because you have to reduce the a um, a net by that particular factor u, and that factor u is a function of your x bar and something called L. We are only talking about x bar. We'll talk about what L is, but that is how you calculate x bar, and these should be available in the um, member property tables. We will do worked out example. That's when we will get into the member property table and find out where all these are. But for now, you just need to understand how to calculate your x bar value. So this is a case when all the elements are connected. This is a case when only where tension load is transmitted to some but not all of the cross sectional elements by fasteners, right? Then this is how you calculate your x bar. If you have a tension member where tension load is transmitted by transverse welds to some but not all the cross section elements, right? So now we are talking about welds, but then we are talking about transverse welds. So that is a scenario. I wish there were a picture here in the code, but then imagine something like this. Imagine you have a gusset plate. Again, there's a tension member, and there's so we are welding only here, right? So P, and we are only welding there. Okay. So when you do that again, only one element, and that element is welded, so U equal to 1.0. Okay. But now we are talking about a case wherein you have a gusset plate like that, and let us say you have a T connected to it. This is the web of the T, correct? This is the tension member, but you are only welding it here, right? So the web of the T is not connected to the gusset plate in any way, but whereas the flange of the T is connected to a transverse weld. So when that happens, meaning if you look at it from this view, then you have a gusset plate. Let's say you have a gusset plate, and here is your T that is connected to the gusset plate, and the T is welded, correct? So when that happens, for your yes, U is 1.0, but then you will have to calculate your A net, and that A net should be only the area of your connected section. This is the area of the connected section that has to be taken into account. Okay. So AN is nothing but area of flange in this case. Okay. So another scenario is when let's say you have your gusset plate like that, and this time instead of a T, you have a channel section that is connected. So this is P, that is your gusset plate, and then it's only welded there. Okay. So when that happens, I mean, if you look at it view from this view, maybe you have a plate like that, and you have a channel connected like this, correct? And the channel, only this part is welded. So when that happens, yes, U is 1.0, but then your A net used in the calculation should be area of just that particular web. So you should not consider this and that in your area calculation. Okay. So if you miss that and you calculate area, there will be an answer wherein the entire area of the channel is also considered, and you will choose that answer. Okay. So one last example is where you have a gusset plate, and then you are welding an angle to it. Maybe this is the angle, right? And the angle is only welded here. That means in this view, maybe you have the plate like that, and your angle is like this. The angle is only welded there. And that happens. Yes, U is 1.0, but then you have to consider your uh, area of that leg for your AN calculation. Okay, and that is what is being discussed here. So when the case 3, all tension members, when tension load is transmitted only by transverse welds to some but not all cross sectional elements. When that happens, U is equal to 1, but AN, area of the of the directly connected element. Okay. Now going to case 4, you have plates, angles, channels with welds at heels, T shape, W shape, with connected elements where the tension load is transmitted by just the longitudinal welds. So if you see an example here, nice little picture here, you apply tension here, there is weld here, there is weld there, correct? When that happens, um, how do you calculate your U area? Again, why should you calculate U area? Not the entire area of the member is effective in calculating the net in taking the tension load. So you have to reduce your A net with a factor called U to calculate your A effective, and that effective area calculation needs U. This is how you calculate your U. U is a function of usually X bar. U is usually a function of X bar and L, but sometimes when in this particular case 4 here, it is a function of your width of the plate as well. Okay, so the width of separation of these two welds. Okay, here on the picture you see L1 and L2, whereas in the calculation you see L. L is nothing but L1 plus L2 by 2, and that is given in the footnote of this particular table here. Okay, so we covered case 4. Now we are going to simpler cases like you have a round tube, and then so this is something like you have a gusset plate and you have that round tube. They slot the round tube, knife edge detail, so that is P, and they weld it there. Okay, you weld it there. You know the diameter D, and then you know the length of your connection. This is important. L is nothing but the length of that connection, correct? The connection is happening over that particular length. You know L, you know D. Then if your L is greater than 1.3 D, then your U is 1. Your L is between these two values. Then you calculate your U based on this. Then you need X bar, and X bar is just a straightforward calculation here. Okay. Case 6, rectangular HSS with a single, so this is called, this is the single concentric gusset plate that they're talking about, or with the two-sided gusset plate. So this is one gusset plate on one side, gusset plate on the other side. So depending upon single concentric gusset plate or two-sided gusset plate, you have different formulas. The formulas are very straightforward. Again, the aim is to calculate U, correct? And the U, unfortunately, is a function of if your L is greater than H, U is from this. If your L is less than H, I don't know what would happen when L is less than H. Okay, so I'll have to check that. But then for cases wherein L greater than H, you can calculate your U, which is a function of X bar, and that X bar is a function of B, D, B and H of this section. You know B, you know H, then you can calculate that. Same thing here, two gusset plates, gusset plate here, gusset plate there. Your U is a function of X bar calculated using this simple formula here. Okay, now we'll go to case 7. These shapes, W, M, S or HP shapes, T's, wherein so if you have these shapes and you have two conditions. If your shape has a flange connected with 3 or more fasteners in the line or direction of the loading, so that means let's say you have you have an I section like that connected with 3 or more fasteners, 1, 2, 3, 4 fasteners to another plate. You're transmitting the tension load to this particular plate here through those fasteners, right? And if my BF is greater than 2 by 3 times of D, then my U is that much. If my BF breadth of flange, if that breadth of flange is less than a certain value, then my U is this much. Okay. So you have to just enter through here and figure out if you are there or if you fall in this category. And then if you are here, then you have to figure out if you are here or here, and then pick your U value. As simple as that. Okay. When you have the web connected with 4 or more fasteners in the direction of the loading, U is that much, straightforward. This is case 7. Moving to case 8. Single double angles. Again, with 4 or more fasteners in the direction of the loading, U is this much. With the 3 fasteners in the direction of the loading, U is equal to that much. Okay, so that's how you calculate your U value. Again, where is U value used? finally eventually we want to calculate uh, you want to calculate your tensile strength, and that tensile strength depends upon tensile yielding. A minimum of tensile is a minimum of these two, tensile yielding or tensile rupture. Yielding, pretty simple, you take gross and then yielding happens on the gross area, so you take gross area times the stress and multiply it with the strength reduction factor. Tensile rupture a little bit complicated. It happens on you need something called a net effective, and that a net effective is nothing but a net times of your u, and that particular u is a function of your, mostly many times it's a function of your x bar and l, and it has a table. You need to understand the configuration of your connection to calculate your uh, strength there. Okay, so that is about this. We'll talk about maybe talk about pin connected sections and then get into problems. Okay, so pin connected sections, uh, again pretty straightforward, nothing there. If we visualize this particular picture, then you can you can see what's happening. Okay, so pin connected structure thing is something. Let's go to this page here. Okay, so pin connected. Okay, so pin connected, you failure modes. There are different failure modes. One is your tensile rupture, and the other one is shear rupture. And then there is something called bearing, and there's something called yielding. Okay, so we'll visualize this and then we'll go to the code to find out the formula. Okay, so pin connector structures are something, I mean, you have a member like that and there is a pin there, right? And then this member is subjected to tension. Okay, the distance from here to here, let us call it a, and the diameter d, this is the diameter d, and there is something called be, which is effective width, be. Okay, so I mean, it is all given, but then be is equal to 2 times of t plus 0.60. T is the thickness of this plate. Okay, so if you know be, now how will this fail? What is tensile rupture? Tensile rupture is uh, um, it rupture, meaning it happens on the effective area, right? Net area. So let us say this section, once you pull, if that section is weaker, then this entire chunk can, this chunk here can come out, right? So how do you calculate that particular strength, right? So we know that this is be, and we know that this is another be, correct? So the area is your 2 times of be times of the thickness of the plate, right? So that is the area, and because this is rupture, you multiply it with your rupture strength, right? But this is the nominal strength, and you multiply rupture with your strength reduction factor to calculate your design rupture strength. Okay, so that is that. So we covered this particular thing here. So the rupture is happening on this area. That is what you need to visualize, right? So now let's talk about the shear rupture. So again, you have the pin connector member like that, right? So this is your diameter hole with the diameter d, and that is that dimension from that edge to the free edge is a. This is your be, and this is your be. Okay, so when that happens, um, let us say you pull this thing, then this particular part can shear off, correct? So that is shear rupture. Okay, so when um, so shear rupture, so what is the area on which this rupture is happening? It is happening, so this is the length, this is another length. What is this length here? That length is a plus d by 2, so a plus d by 2, right? There are two such planes, so 2 times the thickness of the plate is your area of that particular thing, right? And you multiply that with your FU, and then you multiply that with 0.75, right? 0.75 is just the strength reduction factor. FU is the rupture strength. Right, and then this is the area on which that is happening. Okay, so that is what is happening here. Now let's talk about let's talk about bearing. Bearing is when you have your plate like that, right? This is the hole, and then load is being applied. So near the bolt area, you might see bearing failure like that. Okay, and bearing failure, again, we'll see all these formulas, but then that is a function of your projected length, right? So how do I find the bearing thing? It is a function of my projected diameter of the bolt times the thickness of the bolt. That is the area on which that area there, right? You multiply that area with, because this is a bearing failure, it has to do with yielding, and there is a factor 1.8 there. That is your nominal strength. Multiply that with 0.75, which is your bearing related strength reduction factor. Okay, so that's how you calculate bearing. And yielding is pretty straightforward. The last one is yielding. Yielding is, again, you have your uh, let's say you have your plate like that, right? And then you're applying load here. So this part can yield, right? So yielding is pretty straightforward. What you do, you take the width of the plate. So you find out the gross area, which is just the width times the thickness. You multiply it with your Fy. You multiply it with your yielding related strength reduction factor to calculate that strength. So once you find out your tensile rupture, shear rupture, bearing, and yielding strength, you pick your minimum, and that is the strength of your pinned connection. As simple as that, right? And that is what is being described here. If you go here, it says phi Tn or Pn by omega. This is ASD, right? This is LRFD, is the lower value of all these limit state. What are those limit state? Tensile rupture, shear rupture, bearing, and yielding. And we talked about all those things in detail, right? I think what I missed on shear rupture is multiplying with this factor in my previous explanation. And that is because you take Fu is your tensile rupture strength. To convert that into shear rupture strength, you multiply it with a factor of 0.6, right? And then multiply with the area. Okay. But everything else is correct. So this is how you calculate your tensile rupture. This is our straightforward. This is how you calculate your shear rupture. Each limit state has a slightly different phi value, correct? And your ASF, how do you calculate your ASF? The ASF is here. If you don't have to remember all those formulas or the sketches that I drew. What is your effective width? It is here. D is diameter of the pin, not diameter of the hole or anything. T is the thickness of the plate. So given all these things, this is a very straightforward calculation, and if you have that in exam, you must be happy about it. Okay. These are some dimension related information, but I don't think let's jump into some problems. So that completes, in fact, that completes chapter. We talked about every page here. So chapter D, pretty straightforward chapter. We talked about that. We talked about how the A net has to be calculated, correct? We talked about the pin connector members. We talked about how U has to be calculated for all these 7 or 8 different cases here. And for pin connected members, we talked about all the limit state, which is tensile rupture, shear rupture, bearing is in a different section. The formula is not available here, but then you'll have to go to section J7, and then yielding of cross section straightforward. You don't need a formula for that. Okay. Right. So let's see how are we doing on time. Let's see. The idea is to see if we can do a couple of worked out examples, and okay, just 49, 50 minutes. So let's do some worked out examples here. Okay, so example 1, right? Pretty straightforward problem. You have a gusset plate like that, and you have a tension member like this, right? And this tension is being applied. This is your gusset plate, and there are 4 bolts like that. Okay, so the plate is PL half by 5, meaning the width is 5, the thickness is half. Okay, and this is a A36 plate. That means it has an Fy of 36, Fu of 58. Okay, KSI, KSI. Okay, and they have also given us the bolt hole. The bolt diameter is 5 by 8 of an inch. Right? Remember, this is less than 1 inch. Okay, and then to make our life a little bit easier, they said, okay, forget about the U factor. A net uh, is nothing but A effective in this particular case. So we don't have to worry about the U factor and all that. And they're asking us what is the design strength for LRFD. Okay. So we know that the design strength is the least of, you'll have to calculate your yielding and your rupture, right? And the yielding strength, what is your yielding strength? Yielding strength is yielding happens on the gross area. Take the gross area, multiply with Fy, and then phi factor of 0.9, right? Rupture, your phi factor is 0.75, happens on the um, net area. So you need, and it is rupture. So you use Fy and you find out your AE, right? So AG, when you look at this plate, how do you calculate your AG? AG, so that's the plate, right? And we are talking about a failure. When you say gross area, you are talking about a failure there, right? There's no bolt hole deduction, so AG is pretty straightforward calculation. It is 5 times of half, which is 2.5 inch square. That's your AG. Okay. How do you calculate your A net? That's about AG. But how do you calculate A net? A net, that means we are talking about an area which is through that, correct? So A net is nothing but you have that plate, but there are 2 bolt holes, right? So that is your net area, correct? How do you calculate the that area? So this is the thickness of plate, and this is the width of the plate, which is I think which is 5. This is half. Okay, so that is nothing but I mean, to find that, you need to find out what your DH is. DH is the dimension of the hole, because a net is nothing but a gross minus your 2 times, in this case 2 times the DH times the thickness of the plate. So DH is the diameter of the hole, is a function of your it is nothing but your nominal bolt diameter plus a 16th of an inch. Nominal bolt diameter is bolt diameter plus 16th of an inch in this case, because it is the bolt diameter is less than 1 inch, plus you have another 16th of an inch. So DH, if you do all the calculation, so you get your DH as 5 by 8 plus 16, 1 by 16 is 1 by 8. This is 6 by 8 inches. So that's your DH. Okay. So you club the DH, put the DH here. AG is 5 times of um, AG is 2.5 inch square. That is the gross area, which is this one here, minus 2 times of diameter of hole, which is 6 by 8 times of thickness of plate is 0.5, you end up with 1.75 inch square. Okay, so um, so yielding, how do you get the strength? You take 0.9, multiply with your Fy, which is 36, and your A gross. Correct. What is your A gross? A gross is 2.5 inch square. Correct. And then rupture, what you do, you take your 0.75 and Fu, which is 58, then your um, A net, which is this A net, which is 1.75. So the minimum of these two things is your strength. So this one is roughly 81 and that one is 76.125. So this fellow controls. Okay, as simple as that. So you calculate your yielding, you calculate your rupture strength, yielding strength. Again, we are calculating the design. So there is a 0.9 factor, the strength reduction factor that we are applying. Rupture strength reduction factor is 0.75 because rupture is more dangerous, meaning doesn't give you warning. So you want your factor of safety to be slightly high. That means you are reducing the strength a little more. Okay. Yielding happens on the gross area, so that's why you're taking Fy. Rupture happens on the net area. And fortunately, our net area is equal to the effective area. That is because all the elements are connected, right? And you have your Fu as your um, rupture 58 in this case. Okay, so how do you calculate AG? AG is this entire area without any deductions. That is that much. How do you calculate A net? A net is this entire area minus the bolt holes. So A gross, A net is A gross minus some bolt. How many bolt holes? 2 bolt holes. Diameter of the bolt hole, thickness of the material. So right. And how do you calculate the hole diameter? Depends upon the nominal. This is the nominal diameter of the bolt plus another 16th of an inch. Nominal diameter is dB plus 1 by 16 and not dB plus 1 by 8 because the bolt diameter is less than 1 inch. Okay, so you calculate nominal diameter, calculate A net, A gross. This is your A gross, this is your A net, this is your Fu, this is your Fy, this is your strength reduction factor in yielding, this is your strength reduction factor in rupture, and then you find out the strength of the connection as 71.25 kips here. Okay, so that's a pretty straightforward problem. Let's do another problem here, right? Again, you have a gusset plate, you have something like that, you have something like this, and this time we have an angle. Here is this is the tension member, and you have 3 bolt holes like that. Okay, this angle is a L 3.5 by 3.5 by 3/8 of an inch. Okay, that's the thickness of the angle. We have been given this information. The bolt diameter is 7 by 8 of an inch. Okay, material is A36. That means your Fy is 36 and Fu is 58 ksi. This is your Fy. This is your Fu. Okay, and this P is composed of P dead. The dead load is 35 kips. P live. The live load is 15 kips. Okay, and then they have to make our life easier. They said, okay, take in a effective net area as 0.85 times your A net area. That means you don't have to worry about calculating U factor. They have done that for us, and they want us to qualify this connection. Is this connection okay? Can this take these are service loads, but then can that take the factored load? How do you know the connection solution? How do you know if the connection is okay? Your PU factor load should be less than phi times of PT. Okay, so PU, how do you calculate PU? PU is factor load 1.2 times of your 35 plus 1.6 times of your 15. That is your PU, and that should be less than phi times of PT. Okay, so PU comes out to be, this is 66 kips. So that should be less than your phi times of PT. What is phi times of PT? PT, phi PT is the minimum from your yielding and rupture, right? So phi times, so this is the design strength of your tensile strength of your connection. Okay. Now yielding is your 0.9 times of Fy times of A gross, and this is rupture is 0.75 Fu times of A net. Okay. So most of the time you will be spending time calculating the A net. So let's calculate AG. AG is the gross section, gross area of that angle here. So that means its entire section. How do you find out that? You get to table. There are tables in the code, right? So you get to table 1-7 and you find out that the area is 2.5 inch square. That is the gross area of the angle. Which angle? L 3 by 3 by 3.5 by 3.5 by 3 by 8. How did I get the area again? Went to the table and found out that for L 3.5 by 3.5 by 3 by 8, this the area is listed as 2.5 inch square. Okay. Now the interesting part, how do I calculate my net area? The net area is gross area minus something. Minus what? This is gross area minus 3 bolt hole, 3 times there are 3 bolt holes here, right? Actually 1, because we are talking about, yes, there are 3 bolt holes, but we are only talking about that area there. So this is just 1, and that would be the diameter hole times of the thickness of material, whatever it is, right? So how do you find your diameter of the hole? Diameter of the hole is diameter of the bolt. If I go here, what is my DH? DH is nominal diameter of the bolt, which is in this case D bolt plus 1 by 16. Why is that? Plus another 16. Why is the nominal diameter only that much? Because the bolt is 7 by 8 less than 1 inch. Okay, so that is dB plus 1 by 8, which is nothing but dB is 0.875, 7 by 8 plus another 1 by 8 equal to 1.0. So d whole is 1.0. Okay, plug that thing into this equation here. So your A net is equal to A gross minus 1 dB times of thickness is 3/8 of an inch, 3 by 8. Okay, A gross is 2.5 minus 3 by 8 is nothing but 2.125 inch square. So that is your A net. Okay, but once you know A net, you have to calculate AE as 0.85 times of A net. That is what is given in the problem. So 0.85 times your 2.125, roughly 1.80625 inch square. So that is your AE. Now what do you do with AE and AG? You come back here and plug them here. So this one, the rupture strength is 0.75 times of 58 times of my A net, which is nothing but sorry, this is AE. Effective net is A net times of 0.85 given in the problem statement here. So that is 1.80625. Find out that and find out this one. This is 0.9 times of Fy is 36. A gross is 2.5 inch square. So that is, this comes out to be what? This comes out to be 81 kips, whereas this comes out to be 78.75 kips, correct? And PT is a minimum of this and that. So your PT is 78 point, PT is 78.75 kips. Okay. So this is the strength, whereas that is the load that is coming. So 66 less than 78.75, that means we are okay. What is 66? Is your PU. What is 78.5? This is your design strength. one is less than the other, so we are good. Okay. So that is about this problem. Again, what did we do? We were given real quick. We were given a gusset plate and an angle. The size of the angle was given. The diameter of the bolt was given. The material was given, and service loads P dead and P live were given. And I mean, instead of calculating the U, they made our life easier by giving us the definition for AE as 0.85 times of A net. Okay. To how do you decide if the connection is good or not? PU should be less than phi times of PT, like concrete, like anywhere. PU is the ultimate load, that is the demand, that should be less than the design strength. Okay. Now PU factor load is 66. To calculate phi T, I need A gross. A gross is from the tables, is 2.5 inches square. From A gross, I calculate A net. A net as A gross minus something. That something is nothing but the diameter times TW. The diameter of the hole is diameter of the nominal diameter of the bolt plus 16th of an inch. Nominal diameter of bolt is uh, d bolt plus 1/16 because d bolt is less than 16th, less than 1 inch. Okay, so dn. So you subtract that, find out your an. Once you know your an and ag, come here and plug your ag here, and then calculate the yielding strength as that much. Come back here and plug your AE here, and then calculate your rupture strength. Okay, so the minimum of these two is the actual strength of the I mean design strength. So minimum of those two is 78.75, whereas that is less than the loads that the load or the demand that is coming onto this connection. So this connection is good. Okay. We could have done another problem, but then let me just define it and we will skip the problem here. This time we have the two angles like that. There's another angle like that, back to back, and they're connected like this, right? Maybe there's a gusset plate. And then there is a load being, so in other words, if you look at this thing in this view, you have an angle like that. That's your flange, that's this. And there are 1, 2, 3, 4, and then there is a load being applied onto it. Okay. Then now you're asked to find the strength of the connection. Strength of the connection, you have to find your gross area at that location, right? AG, and net area at that location. That is your net area, correct? So to calculate your net area, you take the gross area minus, in this case, 2 bolt dh times of t, right? I equal to 1 to whatever. This summation is happening on 2 because there are 2 bolt holes. Okay, so based on the bolt hole diameter, you find out that, you find out your gross area, you calculate your so this is your net area, right? You multiply with that, you take the net, to convert it to AE, you take your A net, you multiply it with a U factor, okay, and then calculate your yielding and rupture strengths and pick up the minimum value there. Okay, so I want to skip this problem because we can do a problem instead of this straightforward problem here. We can do a problem on um, um, our as to how we can use the U factor, right? So let's say the same problem, there's an angle here, right? And instead of that angle getting bolted, now we have the angle welded at this location here, welded like that, right? Um, so that means it is nothing but from this view, you have a gusset plate like that, and you have your angle. Angle is like this, and it is an angle is only welded here. Or I'll draw that in, right? So the angle is only welded here, right? And then force is applied, right? So as you can see here, not both the elements of the member are connected to the gusset plate. So this load is only traveling through one element, not both elements. Correct. So So the angle here is L 6 by 6 by half. Okay. So, and we are asked to determine the strength of the connection, right? So the solution is you have to find out your gross area. To find out your gross area, you get into the table for this particular shape, and you find out that the gross area is 5.77 inch square. Okay. We are given, I think that the other information given is this is A36. That means your Fy is 36 and Fu 58 KSI. KSI. Okay, Fy 36, Fu 58. Okay, so your A gross is that much. How do you calculate your A net or A effective net is nothing but U factor times of A net, correct? But my A net is 1 second here. Okay, notice here that um, you have both longitudinal welds and transverse welds, right? Um, if you were to only have longitudinal, sorry, you were only to have transverse welds, then U is 1, as we discussed, and we consider the area of just one leg, the connected element. Okay, but in this case, both the longitudinal and transverse welds are connected, so you need to find your U factor. Okay, and you know that U is 1 minus x bar by L, right? X bar is nothing but the centroid of this shape is somewhere here. Okay, and the distance from the plane of transfer of shear to that will become your x bar value. So if you go to the steel manual tables, and then for this particular member here, L6 by 6 by half, it is an equal leg, so you can find out your x bar, and that x bar value is 1.67 from the tables. So 1 minus 1.67. What is the length of connection? The length of connection is the connection is happening on this length, which is 6 inches, looks like in the problem statement. Okay, so when you subtract that here, then you calculate your U value as 0.722, something like that. So once you know your U, you calculate your A effective as U times of A net, which is U is 0.722. Then A net is nothing but A gross in this case 0.77, because there's no deductions for bolt holes, something like that. So this is 4.16 inch square. Okay, now rupture strength, how do you calculate that? You take your rupture phi, you take your Fu, you take your AE, right? So phi for rupture 0.75, Fu in this case is 58 KSI, times of your AE is 4.16 inch square, so that amounts to 180.96 kips. Okay, how do you calculate your yielding? Yielding strength phi factor times your Fy times of A gross. Yielding strength phi factor is better than 0.75, 0.9, 36. My A gross is 5.77, so that amounts to 186.94 kips. Okay, so the strength from rupture point of view is that much. Strength from yielding point of view is this much. The minimum value is this fellow here, right? So this does not control, this controls. Okay, so that's how we calculate the strength of a simple angle connected to a gusset plate with not just the transverse welds but also uh, longitudinal welds. Right? Now there is another important concept that I want to talk about. Let's see if we can finish that. So when you, let's say you have an angle like that, and right, that angle has bolt holes like this. It is connected on both sides to uh, a gusset plate, obviously. So you have a gusset plate on this side, gusset plate on that side. I'm not going to draw that. Um, so let's say this distance here is called is 2.5, and that distance from here to this edge is 3, and this distance is 3.0. Okay. Uh, when something like this is connected to gusset plates on both sides, and you have to calculate your U factor, uh, I mean, you need a net area also. So to calculate the net area, what you do is you unfold this angle. That means you cut this piece here, then unfold it. So when you unfold the angle, you will find a pattern like that, right? So that is the center line, and then these holes are also, they're also zigzag. So these are that's the top section there. There's the center line, and then these holes here are obviously at that location like that. Okay, and we'll do a detailed video about this. But then when the holes are staggered like this, right? There are a couple of rules that you need to follow to calculate your net and gross area, and that is what we'll look in our next session. So the failure can happen on along this plane, right? Or it can happen along this plane like that, right? So we need to calculate different net areas and calculate the least AN. And when you unfold this, there is also a certain rule as to how you calculate. For example, the distance from between these two bolts, which is that bolt and this bolt hole here, is called the gauge distance. And that gauge distance is not a straightforward value, which is just not. Um, I think this is from here to here. It is another 2, right? Or 2.25. Let me see here. Anyway, that to calculate this gauge distance, you need to calculate that distance and this distance, but then subtract one thickness. This is the kind of problem that we will do in the next session. Um, it is pretty detailed and involved, and there are certain rules to see how you can uh, figure out a path or the critical failure plane. Okay. Again, the idea is to find out your A net given the A gross. A gross minus something. That something. How do you calculate that something is a little more trickier when you have staggered holes like this. Okay. If the holes were to be um, like that, then pretty easy, right, to calculate the net area there. But when you have once you have when you have a staggered hole, the length of the failure plane gets increased, um, and the code has some guidelines about how that uh, uh, failure the the net area can be calculated in case of staggered holes. And the main parameters that can come into play is something called the gauge. Sorry, this is the S value, and then the gauge distance of those bolt holes, meaning from here to here, that is one gauge distance. From here to here is the other gauge distance. From here to there is another gauge distance, right? So we need to know what S is, what G is, and how we can calculate the um, A net for a staggered connection. This is what we'll discuss next time. Okay. So in short, um, we talked about tension members, the entire chapter. The main idea is the main content is here, wherein we're trying to figure out um, the tensile strength of a connected member. That tensile strength is the minimum of yielding and rupture, and yielding happens on the gross area, rupture happens on the net area. So you use your gross area and net area, and then you use your Fy and Fu respectively, and use different phi factors. Okay, we are only doing the LRFD. ASD is pretty straightforward. You do the LRFD value and then divide it by 1.5. Okay, let's say you find your LRFD strength, you divide that by 1.5, and then you get your ASD strength there. Okay. So we talked about net area calculations and how this U can be found out from this particular table. We got into all the details of this table here, the 8 different cases, and we talked about all those cases, correct? And then we talked about pin connection members, and then figured out that there are a bunch of limit state, that means tensile rupture, shear rupture, bearing, and yielding. We saw the pictures of different all these different cases, and then we did some worked out examples on how U factor can be calculated on simple connections, and how in a effective can be calculated. Okay, but those are straightforward problems. In the next session, we'll do a little more detailed uh, problem on all this. All right. Thank you.